Do you pronounce this Technion as Technion, or how do you pronounce?
Technion.
Technion, not Tech. It's Technion. It's not Technion. Okay. Yeah, many people will watch later the recording, so don't worry about the people who attend this live or not. So maybe let me also press recording. Welcome everyone to Harvard CMSA Quantum Matter in Math and Physics seminar series. We are delighted to invite Professor Shlomo Razamat from Technion. We'll be speaking about his recent beautiful survey on this paper on the topic of 4D supersymmetric dynamics and the geometry. Let me remind the audience, please feel free to interact with Shlomo and ask questions during his seminar. And let us directly welcome Shlomo. For yours, please take over. Thank you.
Thank you very much, Jovan. Thank you for the introduction and for giving me the opportunity to present this talk. So I will be talking about certain slice in our modern understanding or recent understanding about four-dimensional supersymmetric dynamics and its relation to geometry. And what Jovan asked me to do is to kind of review or overview this overview paper that we have written recently with Eviatar Sabak and Dor Sela, who were my students and are now postdocs, and also with Gabi Tzafrir. So this talk will be a slice of recent progress in this field. So I will not give much details, but I mean technical details, but I will try to give the flavor of things and flavor of the logic and what is being done and what can be done and what are the open problems in this field. So here is the outline of the talk. So I will start with kind of introduction where I will detail the types of questions we are trying to pose and trying to answer and give a flavor of the approaches and types of answers that we are obtaining. So this will be sort of an introduction, and then I will detail the tools, the basic toolkit to deal with the supersymmetric quantum field theories in 4 dimensions. This toolkit will be amazingly small. Okay, basically we will have some techniques that all of which can be related to some kind of counting problems. So they will be very simple, but we will see that one can go do a lot of mileage with this small toolkit. So I will overview these basic tools that one can have at their disposal to deal with these problems. Then we will discuss basic examples of 4-dimensional supersymmetric dynamics, the dynamics we try to understand. And then I will present this program of understanding these dynamics using some geometrical intuition or geometrical tools. So I will do that by discussing or reviewing a certain concrete example, which will be very special, and in a sense one can understand it fully, and I will overview how this can be done. And then I will discuss an algorithm or an approach rather than algorithm that one can use to understand these types of dynamics more generally. And I will finish with several slides on some comments on things that I did not cover in the main part of the talk, and on some big open questions that one can discuss. So feel free to stop me with any questions you might have about this. So let me start with the motivation. So what are types of questions or physics questions that we are trying to understand and to explain? So the questions are rather simple and very conventional. Okay, at least one way to phrase them. So what we're trying to do is given a certain quantum field theory in given number of dimensions, we deform it by a relevant deformation, and it flows to some fixed point in the infrared, and we want to deduce the properties of the infrared fixed point. So this is typically complicated because strong coupling regime might be involved. The theory in the infrared might be strongly coupled. So it is very hard typically to address directly the fixed point in the infrared. Okay, so examples of questions we will nevertheless try to answer is whether, two given quantum field theories that are given in terms of weakly coupled Lagrangians. And in this talk, I will be speaking about continuous quantum field theories, not defined on the lattice, but on a continuous space-time. Whether two such quantum field theories, for example, flow to the same infrared theory. And to be more precise, by same infrared theory, I will not necessarily mean exactly the same theory. I will also include in this definition theories which are related to each other by an exactly marginal deformation. So I might start from some quantum field theory flow to some CFT. That CFT might have an exactly marginal deformation, which means there is a parameter in the theory which we can tune, not breaking conformality. And there is another quantum field theory that flows to the same conformal manifold, to the same space of exactly marginal couplings. So that these two CFTs in the infrared are related by this exactly marginal deformation. Another way to view this is that there is a coupling that we can turn on, say here, fine tune it so we will exactly land on the same point, but I will not require that. So this is an example of an IR duality. Another possibility that can happen is that, say, the two theories describe conformal field theories by themselves, the two Lagrangians. There is no flow involved. If you wish, they are directly describing these 2 points. And then in such a case, if there are two theories residing at different points of this conformal manifold, we will call these two theories conformal dual to each other. Another type of a question is that the theory in the UV that we start with might have some global symmetry group that I will denote by GUV. And the question we will want to understand is what is the symmetry, the global symmetry of the theory in the infrared. Okay, as we will review briefly, these two symmetries don't have to be the same. And in principle, we're interested in all the other properties of the CFT in the infrared, for example, the correlation functions, but we will not be able to say anything about correlation functions. We only will be able to say certain things which are very, very protected, and I will explicitly discuss what I mean by that. Okay, so, yes.
Yes. Question about the conformal manifold. So, can you explain maybe to quantum matter people what parameterize the conformal manifold?
Right. I will say more about this a little bit later, but these are like in a given theory, you can have certain couplings that you can add to the certain operators you can add to the Lagrangian with certain parameters, and these parameters are exactly marginal. So that means that once you turn on these couplings with these parameters, no flow is involved. Like it is a continuous parameter, but it doesn't trigger a renormalization group flow. So various things will depend on this parameter, but there is no flow involved. Okay, this parameter doesn't break conformality. So that's what I mean by that.
Then in that case, how do we know the UV flow to which point on the conformal manifold? Why not just the neighbor points?
So you start here with some choice of couplings, and you start a flow. You land somewhere on the conformal manifold. I don't know where you land. In a sense, say you have some independent way to parameterize the conformal manifold. In general, I will not worry where you are. There are some minor caveats in this statement. For example, if I preserve certain symmetry when I start this flow, in a sense, the fixed point will preserve at least that amount of symmetry, the point where I land on the conformal manifold. When I start moving on the conformal manifold, I might break more symmetry. Okay, so I know something about where I land, and it is constrained by symmetries. But in general, there can be, the loci preserving a given symmetry can be not a point, can be some manifold. So I don't know where I land in this conformal.
And if the global symmetry on the conformal manifold can also be different, then the Tool of Anomalies can also be different.
No, so the global symmetry can change with the conformal with the point on the conformal manifold, but the 't Hooft anomalies of a symmetry is preserved, like say you start going on a conformal manifold and preserve certain symmetry, that 't Hooft anomalies involving the preserved symmetries do not change on the conformal manifold. Of course, there are some symmetries that you explicitly break, so you broken those symmetries, but 't Hooft anomalies, of symmetries that you preserve do not change.
So there is still some characterization of Tool anomalies on a conformal manifold within the largest possible global symmetry.
That's right, exactly. That will be important, very important for what I will say later. There is a notion like of a symmetry preserved on a, let's call it GF, a global symmetry preserved on a general locus of the conformal manifold, and the anomalies of that symmetry are invariants of this conformal manifold. That we will use it later.
Thanks. Thank you very much. And part of the symmetry might be broken, but it will match the Tool anomaly by breaking some part of symmetry for some of the points on the conformal manifold.
That's right. So, yes. So some of the symmetry might be broken, like on a generic locus of the conformal manifold, there might be no symmetry, for example, and then no anomaly to.
No problem. Okay, thanks.
Okay. So this is like very, very conventional set of questions that we want to understand. And of course, we will not ask this in a completely general setup. We will concentrate on 4D physics and supersymmetric physics. So a little bit less conventional question. Basically, it's the same question, but I will phrase it a little bit differently. So in recent years, there has been deduced the existence of a lot of strongly coupled quantum field theories using various techniques for which Lagrangian description is not known. So such theories are typically called non-Lagrangian. So the way we deduce their existence is, for example, by starting from string theory or some grain dynamics and deducing that, you know, some CFT with certain properties in given number of dimensions has to exist. So a question that we will want to understand is whether there is actually a Lagrangian for such quantum field theories, either, you know, flowing directly to the same CFT. So this is a CFT, an abstract CFT, and whether there is a Lagrangian flowing to this CFT, or maybe a deformation of this strongly coupled CFT by some relevant deformation, which flows to the same fixed point or same conformal manifold as some Lagrangian quantum field theory. Okay. And this question becomes very important in the following setup, or the way it usually arises is in the following setup. So it's both a question and a way to answer the question that we have posed. And the way one phrases this question, so in this setup still now, implicitly, we were discussing physics in the same number of dimensions. And that's how we usually think about physics. So we start you know, with some UV theory in a given number of dimensions, d dimensions, for example, here and here, and then we perform some relevant deformation and flow to some another conformal field theory. However, we can consider a more general setup where we have two QFTs and they live in different numbers of dimensions. For example, d tilde here and d tilde minus delta d here. And what we then do, we say, consider some relevant deformation of this quantum field theory and flow to some conformal manifold. And here we take this quantum field theory and place it on some compact space. So in a sense, one can view this compact space as a relevant deformation of the theory. In a sense, we introduce a scale to the theory, and in low energies, we effectively have a lower dimensional quantum field theory. So a question we will ask is whether such cross-dimension dualities exist, okay? And what is exactly the map between these quantum field theories in higher dimensions, this compactification geometry, and quantum field theories Lagrangian weakly coupled description of the theory directly in lower dimensions, whether it exists or does not exist. Okay, and whenever such a correspondence across dimensions exists, you see there is a geometry involved, and we will see that the fact that there is geometry will give us some very nice, simple geometric tools to answer various questions and to understand various facets of strongly coupled dynamics. So here is the very basic explanation how a lot of non-trivial dynamics can be deduced from such geometric setup. And basically, it is summarized in this factorization type of a formula. So the point is, say we try to compactify this higher dimensional theory on some compact space. And in this talk, we will always start from 6 dimensions and end in 4 dimensions. So this compact space will be a 2-dimensional manifold, which is also called a Riemann surface. So say we can construct this Riemann surface as a combination of smaller Riemann surfaces. For example, here is a genus 2 surface, and we can construct it in various ways by combining spheres with 3 holes. We can glue them together in different ways. So if such a decomposition of the surface exists, and we understood what is the cross-dimensional dual of these basic pieces, say these 3 punctured spheres here, then we can build using field theoretic constructions such as turning on some interactions, gauging various symmetries, the theory which is a cross-dimensional dual to this bigger surface. So in this case, we might understand the 3 punctured spheres and from it deduce this higher genus Riemann surface, the cross-dimensional dual of the higher Riemann surface. And this fact that this simple factorization holds, conjecturally holds, and that we can check in many examples, gives us many tools to derive interesting dynamics. For example, as is denoted here, we can geometrically engineer the same surface, the same genus 2 surface in 2 different ways. By gluing these 3 punctured spheres together in 2 different ways, this will result in the same cross-dimensional dual theory, at least living on the same conformal manifold. And for example, if we understand this dictionary between basic pieces and compactifications on basic pieces and 4-dimensional theories, we can predict a lot of examples of dualities, understand a lot of dualities, and examples of emergence of symmetries. And that's what I will try to explain. So the basic picture is like that. So say if you are interested in 4-dimensional physics, and that's what we will do today, and we will be interested in supersymmetric physics in 4 dimensions, it is sometimes worth to go higher in dimensions, to start from higher theories living in higher dimensions, and then compactify them on compact spaces and try to understand, what is the correspondence between these compactifications and Lagrangians in lower dimensions, and these interrelations between theories in different dimensions, across dimensions, dualities, in-dimension dualities, will give us an organizational kind of framework to understand all of these strongly coupled phenomena. And again, the miracle behind all of this will be geometry hidden in these compactification scenarios. And in some sense, once you go higher in dimensions, you have less and less options for interesting interacting physics. And once you go to lower dimensions, you get a richer plethora of phenomena, which you nevertheless can understand using this higher dimensional physics. So there is this field theoretic part of the story. So the highest number of dimensions where supersymmetric, superconformal field theories can live is 6 dimensions. So that is the framework in which we will be operating. However, to fully understand this picture, one needs to go beyond this field theoretic framework to string and M theory. And I will comment on that towards the end of the talk. Okay, so that's what we will try to understand 4-dimensional physics in terms of compactifications of a 6-dimensional.
Excuse me.
Yes.
Question about the relation between the dimensional Hilbert space of the higher dimensional theory and low dimensional theory. In this slide and also in previous slide, how are the dimensional Hilbert space related?
So you can start with so I don't know what do you mean exactly by Hilbert space here, but you can ask what are the operators in the lower dimensional theories, what are the states in the lower dimensional theories as related to other higher dimensional theories. So it is a complicated question. For example, you can start from a local quantum field theory in 6 dimensions. It has some local operators and it can have some extended operators. So then you can ask how you can get a local operator in, say, in 4 dimensions. So one way to do that is, say, smear a local operator in 6 dimensions on, say, this compact surface, like integrate it with some measure, and then you will get a local operator in 4 dimensions. That's a way to get local operators. Another way is to take an extended operator, say a 2-dimensional operator, and wrap it on this surface you compactify. This again will give you a local operator in 4D. So local operators in 4D can come from various sources in high D. Maybe this is more familiar, say if you start from 4 dimensions and compactify it on a circle, you can ask the same question. So again, you can have local operators reducing to local operators, or you can have lines wrapping the circle, which will again reduce to local operators in 3D. So the exact mapping between operators is complicated, but we will consider only some quantities which are in a sense robust, that we can count reliably or easily, let me say, between these different dimensions and use them to predict things and to test them. Does this answer the question?
Along the line, yes, thanks.
Thank you. Okay, so let me start. So this was the general set of questions that we try to understand, and let me start with describing the toolkit, or S toolkit, for where S stands for supersymmetric, to address these questions. And again, I will not give derivations or details of how these tools are derived, only hint to their derivations. And if somebody is interested, we try to review these things in this paper, or either review it explicitly or to point directly to places where explanations and so on can be found. So let me start from tools which don't require supersymmetry. So the amazing tool that we have that exists also for non-supersymmetric theories is the tool of anomalies. Okay, so symmetries are a bit tricky, even if we don't have spontaneous breaking of symmetry in these flows. The fact that you know the symmetry in the UV doesn't mean that you know the symmetry in the infrared. Various things can happen. For example, the symmetry in the infrared can be bigger than the symmetry in the UV. Like, say, a new symmetry might emerge, say the non-abelian structure of the symmetry might be enhanced, and we will see an example of that. Also, some of the symmetry in the UV that you see in the UV might act trivially on the theory in the infrared. So it will act not faithfully, so saying that it is preserved is kind of an empty statement. However, what is interesting is that the anomalies, the 't Hooft anomalies, say for usual continuous symmetries, and that's the only thing we will discuss, are a robust quantity. We can compute them in the UV. So again, we want to understand some properties that we can easily compute in the UV. That's where we have the weakly coupled description, where we have a description in terms of the fields, but we want to learn something about the infrared. And these 't Hooft anomalies, you can just count some fermions, their charges and representations, and deduce, and by this 't Hooft anomaly matching condition, or criterion, the same anomalies have to be present in the infrared. So in recent years, there is a lot of work done on generalizing this old subject of these types of simple anomalies for continuous symmetries to higher form symmetries, to higher group structures, to categorical generalizations. All of these are relevant for the types of constructions I'm going to discuss, but we will not discuss them here. We will only concentrate on simple continuous symmetries and anomalies. Even we will not discuss discrete symmetries, which are extremely important and extremely rich structure. So this we can have without supersymmetry. Now, basically, this is the only robust tool we have for theories without supersymmetry. Now, with supersymmetry, we have more tools. That is the magic of supersymmetry. So one can say that anomalies are just counting. You just count some very simple things in the UV, and this counting has to hold also in the infrared. For supersymmetric theories, this counting can be extended. That's the magic of supersymmetry that we will use. So let me explain how it goes. So that if we have this n=1 supersymmetry in 4 dimensions, we expect to have the super conformal algebra in the infrared. So our theory will flow in many cases to some interacting superconformal field theory, and then it will have this superconformal symmetry. So, for example, there will be some supercharges, which, roughly speaking, square into the momentum. And then when we're in the conformal setup, there is another anti-commuting charge, which is typically called S, which is called the superconformal charge. And it has a nice anti-commutation relation with usual supercharges. And the right-hand side is given in terms of scaling dimension, some rotation symmetry, and very, very importantly, a symmetry which is called an R symmetry. This is the magician in all of this story. So this R symmetry is some U1 symmetry, under which fields in the same supermultiplet are charged differently. Okay, so in supersymmetric theories, fields come in multiplets of difference, with fields of different spins being in the same multiplet. And the R symmetry is such a symmetry so that different components of a superfield are charged differently. And saying it differently, the supercharges that are given here are charged under this R symmetry. This is a global symmetry of the theory. However, it sits in the same algebra as space-time symmetry, such that supersymmetries and translational symmetries, scaling symmetries, and so on. So this gives us a lot of power. Okay. For example, there is one interesting quantity that one might be interested about any theory, and in 4 dimensions, these are the C&A anomalies, which basically, for example, capture the various properties of the stress energy tensor, say when coupled to curved background here. So this is an Euler density, this is the Wild tensor, the square of the Wild tensor. There are the C&A anomalies, and because the stress energy tensor sits together with this R symmetry, one can relate the anomalies, the A and C anomalies in supersymmetric theories, to 't Hooft anomalies of this global symmetry, of this trace R cubed, and so on. Okay, so this is a very powerful result. In general, these are complicated things to compute, but in supersymmetric theories, they are related to 't Hooft anomalies, to simple 't Hooft anomalies, which are usually easier to compute. Importantly, this will be very important for us, this R symmetry that appears here is the R symmetry which appears in the superconformal symmetry group. So again, let me draw I will draw this picture many times. So we start with the UV with some theory. We deform this theory by some relevant deformation and initiate the flow. Say we understand the R symmetry here. This is some CFT, say the R symmetry of which we understand. Then we break conformality by this relevant deformation and we flow. And there is an interesting question of what is the R symmetry in the infrared. If we know this R symmetry in the infrared, we can compute many things, for example, A and C anomalies. And there is actually a way to compute this R symmetry in the infrared, knowing R symmetry in the UV. And this goes under the name of A maximization. And so under various assumptions, the following can be said. So the R symmetry in the infrared is given by some combination of the R symmetry in the UV plus charges under various other U1 global symmetries, non-R symmetries, global symmetries that you can have. Non-R symmetry is the symmetry under which all components of a given superfield or multiplets have the same charge. And then one can build a trial A function with a general mixing of all of the symmetries. And the R symmetry, the superconformal R symmetry in the infrared is determined by a set of very simple equations. So it needs to be extremized, maximized in the infrared here. So again, this is computation that we can perform here. We deduce certain R symmetry, but that R symmetry is the true R symmetry which appears in this superconformal algebra. This whole computation is under the assumption that there are no accidental or emergent U1 symmetry that we cannot see from our computation in UV. So under that assumption, this very, very simple, basically counting computation gives us very non-trivial information about the infrared, and we will see how one can use it. Okay. So there are many other things that one can do in supersymmetric theory. Let me very briefly mention additional one. So many of the magic of supersymmetric theories comes from the fact that various quantities are holomorphic or meromorphic in terms of couplings. Like in general, we can write like a Lagrangian for a theory as combination of two types of terms, like a term which is an integral over full superspace, which is kind of a non-holomorphic piece. And then there is a notion of a superpotential, which is a holomorphic piece about which much can be said. I will not go into it at all. For example, the renormalization of this type of terms is extremely constrained. And yes, Jovan?
Actually, question about the earlier mention about the R symmetry. You only mentioned the U1, but in certain case, maybe extend SUSY, you can also have a non-abelian R symmetry.
That's right.
So
that's
I wonder,
right.
Are you just focusing on SUSY n equal to 1, or?
I will only look on n equal 1 supersymmetric field theory. So you're right, like if we have n equal 2, we have U1 times SU2, and if we extend further supersymmetry, we have further a non-abelian extension of this. So in all of the discussions we will only assume n equal 1 supersymmetry. N equal 2 and n equals 3 and n equals 4 are special case of n equal 1. So all of them have this U1 R symmetry. It might be embedded in different ways in this non-abelian structure, but we will always assume an existence of some U1 R symmetry, okay? And we will discuss
it. Let me just make sure. And this R symmetry is a global symmetry that transforms the supercharge, right?
Right. Yes.
And does it make sense to also consider, is there a possibility of a no continuous R symmetry but just discrete?
No, right. So if you have only supersymmetric algebra, there might be no R symmetry. But if you assume that your theory flows to superconformal R symmetry is part of the algebra. It has to be there. Okay, if you have an n equal 1 superconformal algebra, R symmetry appears on the right-hand side of this algebra, and it is there. Okay?
It must be continuous.
It must be continuous. You might be, like if you start from a UV theory, and you might break the R symmetry in the UV to some discrete group, but then if you flow to say interacting superconformal theory, some R symmetry might be there. It might be hard to understand what it is and how it acts, but it will be there.
And you will be continuous?
Yes.
It will be continuous. Okay. Continuous R symmetry.
That's right. Okay. So, for example, from all of these holomorphic type of techniques and so on, one can deduce very simply a dimension of the conformal manifold of a theory. So, for example, again, usually in non-supersymmetric theories, to understand which deformations don't break conformality and whether they write all non-supersymmetric theories with the conformal manifold, it's a very hard question. One needs to address it, not just to leading order in perturbation theory. One needs to solve this problem very painfully, basically non-perturbatively in these theories. However, in supersymmetric theories, again, the question of determining the conformal manifold and how many, for example, exactly marginal deformations are there can be reduced to a simple counting problem. For example, just list all the marginal couplings, classically marginal couplings that you have, and consider a certain quotient, like this G is the global symmetry of the theory. Build invariance under these global symmetries. The couplings can be thought of as transforming under global symmetry of the theory. Build invariance, holomorphic invariance in this global symmetry group from these marginal couplings, and the number of independent such invariants is the dimension of the conformal manifold. Again, there are simple counting problems that one can deduce from various magic that happens in supersymmetric theories. One thing that I think I didn't mention in the beginning, I will have no references in this talk. Of course, all of this amazing work was done by many people over the last 25 years. There are many papers to cite. All of these citations appear in these lecture notes or review papers. So I chose not to mention any citations during the talk, for example, for this beautiful work. So finally, and yes.
So just make sure, are the theories on the conformal manifold supersymmetric and conformal?
That's right. So the conformal manifolds that we have and for which these type of formulas hold are supersymmetric, and by definition they are conformal. Conformal manifold is it's a parameter space parameterizing conformal theories. Okay, we actually don't know, say, in 4 dimensions of any example, interesting example where you have a conformal manifold without supersymmetry. That would be an interesting thing to understand, whether such things actually exist without supersymmetry.
In 4 dimensions?
Yes.
But how about lower dimensions?
Maybe lower dimensions, you can think of some weird example. We also, like in 4 dimensions, you can, well, if you call, like think about, say, free and Mills theory, which depends on the coupling. It's a free theory, there is a coupling. So in a sense, you have a parameter and you don't need the supersymmetry for that. So there are weird cases that you can construct, but in general, like interesting theories is very hard to construct, such that they will have a continuous tunable parameter without supersymmetry. Okay.
Thanks.
Okay. So a final thing, which is basically a refinement of what we were saying about anomalies, a final tool that we can use is a type of a Witten index. Okay, and what is a Witten index? So we take we say quantize our theory on S3, okay, on some on a space which is S3. This is called a radial quantization of a theory, and then we count states, or count basically operators in our theory with various weights. Okay, so the important thing is that one of the weights is the fermion number. So we weigh fermions and bosons oppositely, and then we can have other parameters which couple to various charges. So here is our hero, the R symmetry. We can have some rotational symmetries, some global symmetries. GF is the global symmetry of the theory, and so on. So it's kind of a thermal partition function of the theory, but with -1 to the f. Okay, and then importantly, what this partition function has is that it is invariant under various continuous deformations of the theory. So the general logic of the Witten index is that there is some supercharge that it is conserved, that commutes with all the charges that appear here, and then this supercharge relates some fermionic and bosonic objects, and if this commutator is not 0, then these things cancel in pairs. And what this thing counts is only objects in our theory which are annihilated by a certain choice of supercharge, Q and Q dagger. And this quantity is robust to continuous deformations. Okay, so one can compute this function. It is very non-trivial function of these fugacities, this thermal partition function with -1 to the f. And again, we can compute it in the UV, but it also tells us something about the infrared. It is invariant of this RG flow, and it tells us something about the infrared. Importantly, in the definition of this partition function, this R symmetry enters. Okay, and then because this R symmetry is part of the superconformal symmetry, if we know the superconformal R symmetry in the infrared using the tools that I have discussed before, we actually directly know something about the operators of the fixed point in the infrared. For example, just by analyzing the superconformal representation theory, basically with sum over states or operators in this theory, and they build representations of the superconformal group, and we can decompose this trace into characters of these representations. What one can deduce is that if one uses the superconformal R symmetry, and there are these 2 parameters Q and P, and one looks at the index at the order QP, like expands the index in powers of Q and P and looks at the order of QP, one finds there that the only operators which can contribute are operators which are marginal here and minus the conserved current. So marginals will appear with a plus sign and currents will appear with a minus sign. So this type of simple computation, which can be done in the UV, if we know there are symmetry in the infrared, tells us, for example, something, and sometimes something very useful about the global symmetry of the infrared theory. Okay, even if it enhances in some non-trivial way, and we will soon see an example. Okay, and again, the caveat here, the little star here, is that we were able to identify the superconformal R symmetry correctly. Okay, so this is the general picture. I just mentioned the supersymmetric index, but there are various other supersymmetric partition functions that one can compute. So these partition functions and some generalizations one can compute for any n=1 theory. For n=2, one has some other partition functions that one can compute. And basically all these counting problems give us some kind of a skeletal description of the field theory that we have in the infrared. You know, sometimes the interesting part is in the mid. So this goes beyond these various bones that this counting problem gives us. But knowing these bones is extremely useful and extremely restrictive. For example, if we conjecture duality between two theories, the skeleton computed for the two theories has to be the same. If the skeleton is different, the conjectural duality is wrong. If the skeletons are the same, it still doesn't mean that our physical conjecture about duality is correct. Okay, but what supersymmetry gives us is that we have a lot of these bones that we can compute, and we can form this skeleton, which is rather detailed. Okay, and that's the magic of supersymmetry. And finally, of course, as in any physical computation, once we have some conjectures about, say, dualities or emergence of symmetry and so on, we can perform a lot of consistency checks, say, study further deformations of the theories, gauging various symmetries, obtaining the same result in two different ways, and performing these consistency checks is the final and maybe most important tool in our supersymmetric toolbox, which of course exists also beyond supersymmetry and so on. So these are the tools that we have, and now I will discuss examples of dynamics that one can have, supersymmetric dynamics, and then we will discuss the geometry behind that dynamics. So any questions about the tools? Okay, so let me give you examples. Yes.
Actually, skeleton picture, just make sure when you draw different part of a skeleton have a different topology. How do you try to emphasize here?
So you're asking about this
yes.
These spaces, yes. So the various counting problems that we have discussed, or some of them, can be thought of computing a partition function of a theory on some compact space. For example, the index that I have discussed, the supersymmetric index, is a supersymmetric partition function on a street line S1.
Yes,
there are other partition functions that we can compute.
No, I get
that
it.
is okay.
Yeah.
Thank you.
And in principle, you can check as many as you want.
Right. So the magic of supersymmetry will happen if you can compute this. You can put this the theory that you have on these spaces, preserving some supersymmetry. Okay. So in general, these are curved backgrounds, and you will break some of the symmetry. So you need to worry to preserve supersymmetry. So if you can preserve some supersymmetry, typically you can deduce. You can compute these things rather easily. Okay.
Then a question, sometimes different manifolds can be relayed by doing some surgeries.
That's right. So these are not completely independent objects. For example, you can consider manifolds with boundaries, and then gluing these manifolds in different ways, you can obtain these partition functions. So there is a whole very, very rich story of constructing these different partition functions in different ways from some building blocks, maybe which are more fundamental. You're
so
right.
Also you see using the surgery to compute partition functions.
That's right. You're right. There are various different techniques. Some of them involve some things like surgery. Some of them involve simple matrix models and so on. But I will not go into that. But only thing I want to stress is that these things are easily computable from the UV. Okay, and they tell you something about the infrared.
And it also does not require the theory to be gap TQFT you can still do surgery in general, even for CFT? Is that
I'm not sure what you like. I'm not sure what you exactly mean by surgery, but you can, for example, you can compute these theories on some. The theory is not gapped. It is some CFT. You can compute the partition function on some manifold with some boundary, and you need to specify some boundary conditions. And then you can glue these building blocks together to compute these indices or partition functions, say of these more symmetric and nicer surfaces for which boundary conditions do not need to be chosen.
Yes, usually if the theory is gapped, when you do surgery, the dimensional Hilbert space on the boundaries of manifold should also be finite, and
that's right.
It's easier to control all the
exactly. So,
right, okay. But if it's gapless or CFT, it
okay, I understand.
In
that sense, like you know, when you put boundary conditions, there is typically there is some finite number of choices, you know, that you can make, and then you know you need to sum over all of them, for example, to compute these types of partition functions.
So there's still finite number of choice.
Right, but for these partition functions, there are no boundary conditions to be chosen, except, you know, for preserving supersymmetry. And you can compute it for any supersymmetric theory, basically. Okay, and you, like, for example, if a theory is gapped by itself, like if a theory is massive, you know, by this logic of computing this supersymmetric index, you are summing over states in the infrared. For a gap theory, you only have the vacuum. This you can compute it in the UV. The theory might look complicated in the UV, but if it is gapped in the infrared, the index better be equal to 1, where 1 is the contribution from the vacuum. Okay, so but if the theory is not gapped, then you will get some non-trivial results from this function. Okay, and then nice exercise to do is just take a field with a mass term and compute this index, and you will see that the index is just equal to 1. That's the simplest example.
I just wonder, so maybe you already say, but just one sentence summarize. Say, suppose it's a supersymmetric conformal theory. You want to compute those index in various manifolds. Do you still can use some surgery tricks to do the computations?
There are geometric tools that you can use that to perform this computation. For example, some very general theories that you can consider. General computations that you can consider is basically reducing the theory to 2 dimensions in some sense, and then performing this computation in 2 dimensions and gluing this, you know, like on some Riemann surfaces, and then gluing these things together to form more complicated spaces. Okay, that's. We can maybe discuss it later.
Thanks. Thank you.
Okay, so let me go to explain, like just giving examples of interesting dynamics that one can have. So I will have an example of Nayar duality, emergence of symmetry, and conformal duality, some simple examples. So this is maybe the most celebrated example of a Nayar duality as SUN Seiberg duality. So here is the statement. So I will denote theories, quantum field theories in 4 dimensions by these funny pictures, which are called Quiver diagrams. So in these pictures, these circles with the letter N inside of them stand for SUN gauge groups. And so there is some gauge group that this theory has, and in particular, it also has some gauge field, mu, and because of supersymmetry, there are some gauginous there. So this implies that there is some particular matter content in this theory and gauge interactions. And then these lines represent bifundamental fields. So the squares will represent global symmetry, so no dynamical fields involved, just a symmetry, and circles are gauge symmetries, where you have a symmetry which is gauge, meaning that there are dynamical fields involved. So what is written here is an SUN gauge theory with an F fundamental quarks and an F anti-fundamental quark. So this is a bifundamental matter content, so there is a fundamental and anti-fundamental here. And the statement of the duality is that this theory in some range of parameters flows to an interacting CFT in the infrared. And there is another theory which looks very similar, but it's different. The gauge group is different. The gauge group is SUNF minus N. And again, you have bifundamental fields, and you have some gauge singlet field, let's call it M, let's call this fields Q and Q tilde, and there is some superpotential of the form Q tilde M. And if you analyze the IR dynamics of this theory, you flow to the same CFT in the infrared. So originally, the checks that motivated this duality were matching of anomalies, various Hooft anomalies, analyzing consistency with our G flows and so on. But over the years, we accumulated a lot of more evidence. For example, we can match the partition functions that we discussed before a couple of minutes ago. You can compute the index here, and obtain that since they are dual to each other, these indices will look very differently, will be represented by very different integrals, for example. But because of the duality, if the duality is correct, these two very non-trivial functions have to be equal. So partition functions, and also this type of dualities appear in many, many different physical contexts. And they are motivated by many different field theoretic and string theoretic constructions. So we are pretty confident that these types of dualities can be correct, because there is no proof of such dualities. We only, in a sense, know this picture. Very detailed, a lot of bones in this skeleton, but still the bones. Okay, so this is an example of this Seiberg duality. And we will see how this Seiberg duality emerges in a geometric picture a bit later on. Okay, I'm a bit slow. Sorry about that. So another simple example is of emergence of symmetry. So one can consider this extremely simple gauge theory, SU2 gauge theory with 8 fundamentals. And we split these 8 fundamentals into 2 plus 6. Okay, so we denote these fields by, say, Q and Q tilde. And there are gauge singlet fields, let's call them phi and phi tilde, and we turn on some interaction, some superpotential. This superpotential breaks the symmetry between of rotating these 8 fundamental fields into U1 times SU2 times SU6. So in the UV, this theory has global symmetry, which is U1 times SU2 times SU6, in addition to the R symmetry that we have discussed before. Now, we can perform this computation of understanding what the R symmetry is in the infrared, and modulo the assumption that no funny U1 symmetry arises in the infrared that we completely don't see in the UV, we can deduce that the global symmetry of this theory actually enhances to U1 times C6. Okay, so for this extremely simple theory, the way you can deduce that is, for example, you compute a supersymmetric index or superconformal index and look at this order QP that I mentioned, where you can see conserved currents minus the marginal deformations. And you see that what appears there is the 1, which can be identified with the conserved current of the U1, the conserved current for the SU6, the conserved current for the SU2, and then you see some additional operators appearing. Since here the currents appear with a plus sign, these have to be parts of some bigger conserved current. And in fact, these representations form a representation of E6. That's how you decompose an E6 group into representations of SU6 times SU2. So you don't see it in the UV, but using these simple counting techniques, you can deduce that this simple theory has this enhanced symmetry in the infrared. Again, it's not a proof because there is some assumption going into it, basically that we identify the R symmetry correctly, but it is a very strong evidence that this theory has this symmetry. And again, this can be also deduced from geometric constructions that I will discuss soon. Okay, any questions about this? Okay.
By the way, don't worry about the time. Just take your time. It would be great to good lecture for everyone. Thank you.
Thank you. Okay. So finally, another thing that I want to show you, which I really like, is a way to derive conformal duals. Again, just by looking at this very, very simple counting technique. So let us consider the following exercise. Say somebody gives me a theory, I will call it T1, and this person gives me a lot of information about this theory. I don't need a Lagrangian. Say the person tells me what are the A and C anomalies that we mentioned before. Say what are the indices? What is the conformal manifold of this theory? What is the symmetry preserved on the conformal manifold? What are the various 't Hooft anomalies for this global symmetry preserved on the conformal manifold? Maybe also this counting of operators using indices. So say this information is given to me. And I ask the following question. This is some abstract theory, but can it be that somewhere on this conformal manifold, there is a description of the theory using free fields, like a conformal Lagrangian, a Lagrangian which doesn't flow, a Lagrangian which involves gauge fields and matter fields with some interactions. So using these counting techniques that we discussed, we can actually try to answer this question. Say there is such a conformal Lagrangian somewhere. Then we can compute this A anomaly and C anomaly, which are invariants of this conformal manifold, because they are related to these 't Hooft anomalies of our symmetry. We can compute them in this very simple way. If there is some gauge group, it has some dimension, there is some number of vector fields. If they are free, they contribute in a very particular way to this conformal manifold, to these conformal anomalies, to A and C anomalies. So it's given by this AV times the number of vector fields, and by A chi times the dimension of representation, number of matter fields. So we have here two parameters, A and C, and two things which kind of determine in the most basic way our Lagrangian, our conformal Lagrangian, the size of the gauge group and number of the matter field. So we can solve for these two numbers. Okay, if these two numbers given this A and C turn out to be fractional, that's it. That means that there is no point on the conformal manifold which is directly described by a gauge theory. Maybe there is another gauge theory which flows to this conformal manifold, but there is no point on this conformal manifold which is directly described by a conformal gauge theory. If these numbers are integer, we can now write all the possible conformal Lagrangian with this number of gauge fields and this number of matter fields. This will be a finite list. And out of this finite list, we can compute other counting problems, the anomalies, the symmetries, the dimension of conformal manifolds, indices, and so on. And we might find in this finite list a theory which meets all the criteria, agrees with all of these quantities, or not find such a thing. If we don't find, again, there is no point on the conformal manifold which is described by a conformal gauge theory. And if we find, we can claim that there is a conjectural conformal dual of our abstractly defined quantum field theory. So this is very abstract, so let me give you an example. For example, consider a weird theory. Say, take a gauge theory to be a gauge symmetry to be G2, and take matter to be, say, 3 fields in the fundamental representation of G2, which is 7-dimensional, and 1 field in 27-dimensional representation. This theory happens to be conformal gauge theory. It doesn't flow, okay? And it has a conformal manifold, which is 3-dimensional. It has, on the generic point of this conformal manifold, some symmetry is preserved, and you can compute 't Hooft anomalies of this symmetry. Now you can ask, is there a different gauge theory which describes the same conformal manifold? So here we actually know that the dimension of group is 14 and the number of fields is 48 just by counting, okay, here. So we are after a gauge theory which has 14 gauge fields. So what we can do is we just scan through all the possible gauge groups, and we try to build these 14 from dimensions of smaller gauge groups. So here we can build 14 basically in a unique way as a sum of 2 SU2s and an SU3. And here is a Quiver theory, this theory with gauge groups and bifundamentals. And here actually there are also fields in the symmetric representation of SU3, which has the same number of gauge fields, so 3 plus 3 plus 8, which is 14, and the same number of matter fields, which is 48. And you can verify, analyze this theory, and this theory has a 3-dimensional conformal manifold with SU2 symmetry preserved on a generic point of the conformal manifold, although at the free point, the symmetry is much bigger. For example, you have SU3 rotating these fields, another SU2 rotating these fields, SU2 rotating these fields. But on the conformal manifold, once you turn on exactly marginal deformations, all these symmetries are broken to some diagonal SU2 symmetry. So you can compute all of this counting problem, all of these various counting computations that we have discussed, and all of them agree between these two theories. So the skeleton of this theory agrees with the skeleton of this theory. So one can then conjecture that these two theories are conformal dual to each other. Okay, so this is maybe hard to guess, but again, just counting things, this is something which is very easy to derive. Okay, so with this example, let me move to the how to understand this, all of these properties geometrically. Just to say in advance, this kind of a duality we don't understand geometrically by tools that I will present, but this property, the enhancement of this theory 2E6, can be understood geometrically by the tools that I will present, and this also duality can be understood geometrically. So there are many things that we can understand by this geometrization that I'm going to present, but not everything. Okay, hopefully someday everything will be understood. Okay, so let me go to this final main part of this talk and this description of geometrization of the dynamics. Okay. So again, just to remind you the slide that I had before, the framework in which we are going to operate is the following. We will not just be interested in understanding dualities between theories in the same number of dimensions, but we will try to understand dualities across dimensions. Okay. We will start from a theory, say, in higher dimensions, in d tilde equals 6 in particular, and compactify it on a two-dimensional surface, generic two-dimensional surface, and we'll try to understand what happens in 4D, and in particular, whether there is an alternative four-dimensional Lagrangian description of the theory that we will obtain in the infrared. So here is the setup again. We start from a 6D theory. There is a variety of 6D supersymmetric theories we can choose from. So we choose one theory. We deform it by placing it on a two-dimensional compact geometry. In addition to placing it on compact geometry, we can turn on various background fields. So this 6D theory might have some global symmetry, which I denote here by GUV. And we can turn on, for example, flux for various abelian subgroups of this six-dimensional symmetry supported on this two-dimensional surface. Then in the infrared, we obtain effectively a four-dimensional quantum field theory. Okay? It is abstractly defined in terms of this choice of the 6D theory and choice of this compactification geometry. So this four-dimensional theory is determined in terms of geometry. Okay? These six-dimensional theories are strongly coupled. We don't have a useful Lagrangian description of them, so it is a rather abstract definition. Okay? Importantly, we can compute various counting problems or computations for these 6D theories, even though these theories are strongly coupled, and we can use these counting problems or computations to predict various properties of this infrared theory. And then what we will ask, is there a four-dimensional weakly coupled theory which flows to the same CFT, which here is defined abstractly through geometry, and here we will define it through Lagrange. And the point is that if we find such a dictionary between geometry, geometric construction of theories, and Lagrangian definition of the theories, a lot of these properties of like infrared properties of the flows of these Lagrangian theories in 4D will be encoded in this compactification geometry. A lot of this non-trivial emergence of symmetries and dualities and so on will be easily understood through this geometrical labeling the fixed points. Okay. So let me give you, before giving you an example in detail, yes, there is a question?
Oh, yes. Just make sure the geometry, you mean is just a 2D geometry with possible fluxes. That's the geometry you mean from the 60s?
That's right. That's right. So the geometry which parameterizes this theory, this theory in the infrared in 4D, is the surface, the 2D geometry, plus the fluxes and holonomies and so on. You can think of it like as a generalized geometry. All these background fields are kind of defining this geometry, both fluxes and the surface.
No problem. Maybe a related question. Do people consider possible non-orientable manifolds for these two manifolds, like RP2, etc., for the compactifications?
Yeah, I don't know.
Even Klein-Bart or whatever. I don't know. I'm just asking.
Yeah, I don't have an answer from the top of my head. You might consider various things. You might be worried whether you can put your theory on such surfaces and so on. And so I don't have a good answer.
These are related to a question, say, how do we know stuff from 6D theory do this computation? The 4D theory also is a consistent theory. How do you, for example, if it's a torus, then maybe there are some KK modes, and perhaps the circle is small, and the KK modes might be
That's
have
right.
a larger gap
Right.
that you can isolate.
So, you know, it's a field theoretic construction you can consider. You just take your theory, you put it on a compact space. That you can do. Then the question is, what is this theory in the infrared? So basically you're asking, how do you know this is an interesting interacting theory? It's not gapped, maybe it's free. It can be anything.
But I say, how do you know even it's a consistent theory? Just say that how do you know this complication give rise to consistent theory, not something like maybe not stable, so maybe
it is consistent in the sense that it is always UV completed by the 6D theory, by definition. You start from the 6D theory and you compactify, and it is always UV completed by the 6D theory.
That's true. 6D is complete, but maybe the 4D description might not be a good.
That's right. Well, okay, right. For example, a setup, and I will mention it later, where a simpler setup where this happens, if you put a 6D theory on a circle, okay. In some cases, on a circle, you know, on one dimension there is only one geometry which is compact is a circle, but you can turn on the holonomies for various symmetries, and depending on these holonomies, you might get gauge theory descriptions in 5D, okay? And these gauge theory descriptions in 5D are not UV complete in 5D. You know, to UV complete them, the only UV completions is the 6D theory in certain cases, okay? In some cases, there are 5D theories which UV completed, but generically, the only UV completion is the 6D theory. So what is the property of this 4D theory? Like, what is it exactly? What are its properties needs to be analyzed in detail.
Yes, I think these are also related to, I asked earlier about the Hilbert space of a different dimensional theory.
Right.
I just want to say, maybe you are trying to answer this, but I feel like maybe there's a short statement say, how do you know whether the 6D theory to 4D, this possible communication with fluxes, what are the conditions on the geometry to make sure the resulting compactified theory is kind of a possible some fixed point in the 4D theory instead of some.
It will be, you know, it's well defined. You will get some effective field theory in 4 dimensions. You are asking how many fields you have and so on. I don't have a very sharp statement. You know, there might be, it might be described by infrared free theory, by free fields, and I will soon have an example. There are various possibilities there. You know, the interesting cases is when we have a CFT, and we have a large number of examples when we have a CFT, an interacting CFT. I don't have a very sharp statement when it happens.
Also, another thing is that the geometry, does the size of that two manifold matter?
That's right. So this is a very good question. So we go to, you know, the size sets some scale. So we go far below that scale. So we go below that scale, we lose that scale. Okay, in a sense.
Okay, no problem. How about just another last question? How about do people start from AD theory to do maybe compatible to 4D? For maybe
Which
they put
theory?
from AD. Maybe there's also some AD. Maybe I don't know what is SCFT or S supergravity.
8D? No,
AD.
so in the maximal number of dimensions where super conformal field theories exist is 6 dimensions. Okay, so
there could be also be some AD sugra or some other.
Right. So you can start. Can go beyond the setup of quantum field theory. You can have more general setups, and you can consider that. You can start from string theory, and do various things and go to various regimes. We will not do that. You can do that.
Do people start from AD sugra to give some 4D?
I don't know in particular about AD, but you can definitely do many string theoretic constructions to go to lower dimensions.
Thank you.
Okay, so let me give you a couple of examples, which are very simple. And the first one we will discuss in detail, and this is another example. So for example, you choose certain quantum field theory in 6 dimensions, which has some name, it doesn't matter. And importantly, what you know about this theory is all these counting problems that I mentioned, from which you can make certain predictions about 4 dimensions. So this is the starting point. And say you compactify this theory on a sphere with 3 punctures. Punctures are like holes in the surface, and I will say a bit more about that, and with very particular values of flux. And then you can deduce, and I will discuss this today, that the theory you obtain in the infrared in 4 dimensions has a different description, an IR dual directly in 4 dimensions, which is just this SQCD with SU3 gauge group and 6 fundamentals and 6 anti-fundamentals. So very simple theory. You start with some complicated theory in 6D, you compactify it on a complicated surface, and then you get some rather simple but non-trivial interacting theory in the infrared. Here is another example. You take a different type of a 6D theory. It is a different theory in 6 dimensions. You compactify it basically on the same type of surface. You can deduce, again, that the theory in 4 dimensions is rather simple. It's SU5 with 10 fundamentals and 10 anti-fundamentals and some superpotential. For example, this superpotential is irrelevant in 4 dimensions. So you can think again that, there is a weakly coupled theory you can define, an effective field theory you can define in 4 dimensions with this superpotential and this matter content, and it flows to the same conformal manifold as starting from this 6D SCFT and deforming it by geometry. Okay, so if you are worried about UV completion of this superpotential, you can always think of it as being completed by this 6-dimensional theory. So let me give several examples of what kind of dynamics you can deduce from this geometric understanding. So for example, in this case, we understand this 3D theory, sorry, the 4D theory, when you compactify on a 3-puncture sphere. Now you can take, say, 2 copies of such theories and glue them together. You glue them together along these holes. I say a bit more concretely what it means. And in field theory, it corresponds to gauging various symmetries. Again, I will soon say how to do it explicitly. And you can do it in 2 different ways. Again, either taking these two guys and gluing them along 3 punctures like that, or you can glue a surface to itself and have 1 puncture left and then glue 2 copies of this thing together. You will obtain 2 different theories, okay, 2 different looking theories with different Lagrangians, both SU3 gauge groups, but different type of matter. Bifundamental matter here, some additional fundamentals, but here you have fields in a symmetric representation and in a symmetric bar representation. If this identification is correct, okay, since these 2 surfaces are basically the same, they are the same geometrical objects, we expect these 2 theories to be the same, okay, in the sense that they describe the same conformal manifold. So these 2 different looking theories are now expected to be conformal dual to each other. And you can verify that, again, by computing this skeleton that we discussed. Indeed, you find that everything, the skeleton of this theory agrees with the skeleton of this theory. So this is a geometric way to discover a duality. Another thing one can do, and this goes to this cyber duality that we have discussed. For example, one can take the same 6D theory that we have discussed, this D4 minimal conformal method theory, compactify it on a two-puncture sphere with very particular value of flux. And then the claim is that the theory in 4D is just some West-Zumino theory. So again, you have these bifundamental fields, which are coupled with some superpotential, but you don't have gauge interactions. So basically free fields, okay? Then you can just combine two puncture spheres together to another two puncture sphere. Just glue along this puncture. And the only difference between this object and this object, this combined object, is the value of flux. This theory in 6 dimensions has an E8 global symmetry, and we turn a very, very particular flux for the Cartan of this E8 global symmetry. And now we glue these two things in certain ways so that flux is added in certain way. And the flux of the combined theory looks different than this flux. However, inside E8, this vector of fluxes and this vector of fluxes are equivalent. They are related by the Weyl group of E8. Okay, so from the point of view of 6D compactification, this theory and gluing two copies together in particular way is exactly the same thing. However, field theoretically, gluing means gauging some symmetry. So the theory that you obtain by doing this is a gauge theory with SU2 gauge group and some fundamental matter and some gauge singlet fields. And the demand that these two things are the same comes from these geometrical considerations, and it boils down to very well-known example of cyber duality. So this is SU2 gauge theory with an F equals 6, and this is and it is dual to a collection of free fields basically, and this is the statement of this duality. So again, from geometrical considerations, you could predict this type of duality. Okay, although this was, of course, this is an example of duality, which is maybe one of the first dualities which is known for many, many years by now, almost 30 years by now. Okay, so let me now try to derive this type of duality, this duality for this D4 conformal matter, and I will do it using two approaches, one less systematic and another more systematic an algorithm. So the less systematic is just following the same idea that we described before here, discussing this, discussed on this slide. So we will consider this compactification of a 6D theory on some genus, G-Riemann surface as some abstractly defined theory. And we can compute, as I will discuss, various things about this theory, for example, conformal anomalies, and we will seek for the conformal dual of this theory, very much like we had here. But now this theory on one side, this theory T1, will be abstractly defined as a compactification of some 6D theory, and we will look for a Lagrangian, alternative Lagrangian directly in 4 dimensions. Okay, so this is what we will do. So one thing about this 6D theory that we know, we can compute its anomaly polynomial. Okay, given its anomaly polynomial, we can obtain the anomaly polynomial of the theory obtained in the compactification. Basically, we need to integrate the 8-form anomaly polynomial in 6 dimensions to obtain the 6-form anomaly polynomial. And from it, we can deduce the A and C anomalies. And they are given by these simple numbers, which depend on the genus of the surface on which we compactify this 6D theory. We can play this game that I discussed before of looking for a conformal theory, and we deduce immediately the dimension of the gauge group, if such a conformal dual exists, has to be 16 times G minus 1, and dimension of representation 81 times G minus 1. These numbers are integer, so there is a chance that there is such a conformal dual. That's as specified to G equals 2, so the dimension of gauge group is 16. 16 is 8 plus 8. You can do it in other ways, and 8, where 8 is the dimension of SU3. So we might be able to find the conformal dual of this theory using SU3 gauge groups. And indeed one can do that. So this quiver theory, where we have 2G minus 2 SU3 gauge nodes and this pattern of bifundamental and fundamental fields, matches these anomalies. It is conformally invariant, as we assume when we play this game. And in fact, it matches other expectations that I will detail on the next slide. But to stress, the claim is that compactifying this D4 minimal conformal 6D theory, minimal D4 minimal conformal matter theory on a genus G surface without turning on any flux, this is the theory that one obtains conjecturally. Okay? Since we don't break any symmetry where we didn't turn on any flux, we expect that on the conformal manifold of this theory, there will be somewhere a locus which will preserve the global symmetry of the 6D SCFT, which is E8, as I mentioned before. So here is the picture. We have an abstractly defined CFT coming from 6 dimensions, and we have conjecturally a conformal dual of this theory. There is nothing E80 about this theory, okay? E8 is a weird, interesting group, but you wouldn't guess that this theory has an E8 symmetry. However, analyzing various properties like the dimension of the conformal manifold, the symmetry preserved on various loci of this conformal manifold, that, for example, you can choose it to be SU9, you deduce that it is consistent that there is somewhere on this conformal manifold a locus with preserved E8 symmetry. Okay, so there are two non-trivial claims here. First, this is a cross-dimensional dual of a compactification of the E-string theory. And second is that this theory, somewhere on its conformal manifold, has an E8 global symmetry. Okay, so these are conjectures that you can check in various ways. Okay, so say specializing to genus 2, where the theory that we obtained on the previous slide can be drawn in a simpler way. We can try to find other conformal duals for this theory. Okay, for example, there is a very suggestive way to draw this quiver. There are these 3 bifundamental fields. Let us draw them like that, and there are these 9 fundamental fields. And this mimics the structure of genus 2 surface. We're on genus 2. So we can try to look for another type of theory, which has, again, the same skeleton as this theory. And we find this particular quiver. And again, this quiver we can write in a suggestive way. So there is this field in a symmetric representation. And here, instead of 9 fields in the fundamental, we have 10 fields in the fundamental. But we can think of these extra fundamental fields relative to here and this field in a symmetric representation as something which is obtained if we multiply a fundamental field by a fundamental field. Okay, this decomposes into an anti-fundamental plus a field in the symmetric representation. Okay, and again, this has this suggestive structure of this is a field in fundamental times fundamental of this SU3, and there is this bifundamental and another field like that. So this has the structure of the quiver drawn here. Okay, so this is the duality I mentioned before. Okay, and just by looking at this way of representing this duality, we might think that there has to be a way to break these lines appearing here to build a theory corresponding to a 3-punctured sphere. Okay, and that's what we will do next. Okay, is there any question about this?
Actually, maybe just make sure I really understand the geometry layer. Is the non-trivial cycle on the genus number has anything to do with the graph which you draw in the quiver type of a diagram or something? Are they related?
So, usually no, but here there is a very suggestive picture that it seems that it does, and we will soon see that why it does. Okay, but in general, this is not the case. Okay, in general, you have some quiver, you have some fields, and they don't mimic the structure of the Riemann surface. Here, as I said, we will derive, this statement basically, that this theory corresponds to a 3-punctured sphere in a non-systematic way, by just doing some computation and noticing some features. So we did a very simple counting problem, and you know, we solved that problem. We obtained some quiver theory, and now we are playing with it. And we see that there is a structure which mimics this Riemann surface, and we will deduce something from it in a moment. And in this case, yes, you can think of it as a quiver drawn on this Riemann surface, but this is a non-generalizable statement. Okay, this is just a feature of this particular construction.
Thank you. Nice.
Okay. Okay, so just a very, very quick interlude. So what we will want to do is that we have this closed Riemann surface, and we will want to break it into 3 punctured spheres. So in order to do that, I need to a little bit explain what are the punctures. How should we think about the punctures on the Riemann surface? So I will do it. There is a lot to say about it. It's a very rich story, so I will be very, very quick. So the way to understand the punctures in the compactifications of a given 6D theory is like that. You take your 6D theory and compactify it on a circle to 5 dimensions. If you turn on very particular types of holonomies on the circle, you might end up with an effective field theory in 5 dimensions, which is a gauge theory. Okay, and again, it's UV completed in 6D, as I mentioned before. Then a puncture in this setup you can understand as taking this, you know, 6D theory on a cylinder, and then cutting the cylinder somewhere, and creating this type of a hole of a puncture, and specifying now very particular boundary conditions there. So there are some choices to be made, and there is a very canonical choice which preserves certain supersymmetry. Again, I will not go into that. One can read in this in the papers on the subject and in the review. But the point is that once we perform this very canonical boundary choice, basically we freeze the 5D gauge symmetry at the boundary. So a puncture in this compactification comes with a global symmetry which corresponds to the gauge symmetry of the 5D description. In the case of this E-string that we are discussing now, the gauge theory description is in terms of SU2 gauge group with some matter field. This is a 5D description. So we will expect each puncture to come with an additional factor of global symmetry, which is an SU2 global symmetry. Okay, and then when we glue 2 theories together along these punctures, as we have mentioned before, basically what we are doing, we are bringing these 2 boundaries together, and we are undoing the boundary condition. So we've frozen the 5D gauge symmetry on this boundary. So undoing that will amount to gauging this symmetry. So gluing 2 theories together amounts to gauging symmetry associated to the punctures. And depending on exactly what we do, and again, I will not go into details, you might need to add additional fields and turn on some superpotentials, but the gauging is basically the important thing. Okay, so in this picture, we now understand that if we want to understand this as gluing of 3 punctured spheres together, when we break this picture, we need to have some SU2 gaugings on these edges, maybe with a very particular matter content. Okay, and that's what we will do now. So we will take this theory, which again corresponds to a genus 2 surface, and we will try to break along this triplet of lines. And here comes an important ingredient, again known from the 90s, that if you take this particular gauge theory, this is an example of Seiberg duality that I mentioned, such that the number of flavors on matter is 1 more than the number of colors, the theory is dual to a West-Zumino model. This is again, I mentioned already before. And if we take n equals 1 here, we have this piece with SU3, and the gauge theory is SU2. That's exactly what we want. We have this bifundamental between 2 SU3s, and we have these triangles, and we will be able to exchange it with a gauge theory which has an SU2 here. Okay, so that's what we do. We take this guy and we exchange 1 triangle with this gauging of SU2 with 3 fundamentals. It's just an IR duality. These 2 theories are IR equivalent to each other. Then we do it for an additional line and an additional line. Okay, and then basically the statement is that this theory is IR equivalent because of Seiberg duality to this theory. But now this guy has exactly the structure that we want. it has 3 SU2 gaugings along of these lines, and we can think of it as 2 3-punctured spheres glued together. So finally, the statement is that the 3-punctured sphere with very particular flux, which is to be determined, is just SU3 SQCD with 6 flavors. You know, the way it is, this is the matter content of each one of these 2 pieces here. Again, there are many consistency checks that one can perform. For example, one can count symmetries and so on and check how they're embedded in 6D symmetries, and all happens to be consistent. Once we have these 3-punctured spheres, we can glue them together in different ways. So here, basically, by the rules of gluing these 3-punctured spheres and identifying the fluxes using details that I did not review, the way you identify the flux you associate to this part and this part is opposite, so that the flux of the complete theory is 0. Okay, I'm being very, very fast here. But you can glue things a little bit together. This is something to do with which matter fields you introduce, which superpotential you turn on. When you undo this, these boundary conditions, you can actually construct a theory with which will correspond to compactification on the same genus to surface, but with a different flux, twice the flux which is associated to each one of the pieces. Okay, so you can do that. You obtain some 4-dimensional theory. It will be some more complicated quantum field theory, but a field theory which has a Lagrangian. You can compute, for example, A and C anomalies of that theory directly from a Lagrangian. It will be some weird numbers which are written here. And then you can ask whether there is a 6D compactification on a genus 2 surface with flux, which will give exactly these anomalies. And it turns out that there is. You can turn on a flux in a U1 inside E8 global symmetry of the 6D theory, preserving an E7, and the theory in 4D that you will obtain will preserve exactly this flux. Okay. Now you expect that this theory, this explicit field theory you obtain in 4D, to have, to correspond to compactification, which preserves E7 times U1 symmetry. You can now go, for example, and compute superconformal indices of this explicit field theory you have in 4 dimensions and see whether it is consistent with the 7 symmetry. This is rather non-trivial, but these superconformal indices, again, count operators in the 4D theory. You write them in terms of characters of superconformal group and the global symmetry group of the 4-dimensional theory, and you can see that representation of E7 appear, although you obtain this explicit theory by playing with this, gluing 2 copies of this SU3 with 6 flavors in a very particular way, and there is no E7 here to be found. Okay, but again, you find an E7 in a very, very consistent way with the identification of this theory, SU3 with 6 flavors, as the theory corresponding to the 3-punctured sphere. Okay, this is very fast, but I hope you get the flavor of the argument. This is something actually which is not that hard to follow all the details in detail. Okay, any questions about this? Okay, Juven, how much do I have left?
I really suggest you take your time to say everything, because this is a very nice lecture for many people. Actually, I heard many people are watching on YouTube. So
thank you.
Please take your time.
Okay, so yes. So this was kind of, yes. Okay, so this was kind of an ad hoc derivation. Again, there was some magic. It was not systematic, as I said. So let me now discuss a kind of a more algorithmic approach. Okay, as you will see, it's not completely algorithmic, but one can actually come up with a rather algorithmic approach to discuss many compactifications. And the compactification we discuss will be a special case of that. Okay, so let me detail here a general algorithm. Okay, it's not the algorithm, it's an algorithm, and it's not really an algorithm, it's really an approach. There are some parts of the algorithm which are not systematic, but involve some educated guesses to be made, as I will detail. So what is the algorithm? So what do we want is we want to derive this relation between 6D compactifications, like given a surface and the 6D theory, we want to understand what are the 4D Lagrangians for general compactification. So what we do, take all 6D theories you know, okay, or as much as you can swallow, and compute all the counting problems about this theory. So compute the anomalies and understand the symmetries, I don't know, try to derive the spectrum of operators and so on, okay? At least for some sequences of the 6-dimensional theories. Then in step 2, reduce the 6D theory on a circle down to 5 dimensions, okay? In certain cases, with various holonomies, as we mentioned, you might get a 5D gauge theory in 5 dimensions. This 5D gauge theory will determine the types of punctures you can have and types of symmetries that you can have associated to the punctures that you, and along the punctures later, you will be able to glue various surfaces together to construct more complicated surfaces. Okay, so these 2 steps we discussed in a sense in the examples we had before. And now come 2 non-trivial steps. Okay, so claim number 1 is that if you want to understand the theory which you would associate to a 2-punctured sphere with a flux, you actually need to understand certain domain walls in 5-dimensional gauge theory that you explicitly constructed in step 2. Okay, so let me explain this here. So what you do is that upon compactification on a circle with certain holonomy for a global symmetry, you obtain a 5D gauge theory. But now imagine varying this holonomy for this global symmetry along the 5th dimension. Okay, if you have a holonomy which depends on one of the coordinates, basically what you have flux non-trivial f supported on this, on the surface which is spanned by the circle on which you compactified and the 5th dimension. Okay, so space varying holonomy engineers for you a flux. Okay, now different values of holonomies in various limits correspond to different gauge theory descriptions of this compactification. So in this region you will have one gauge theory description in 5 dimensions. In this you will get another, and there will be a domain wall interpolating the 2. So basically you can take a limit where the holonomy jumps at some locus. Okay, and then you can try to understand what is the 4D theory living on this domain wall. So again, the geometry is that you have a tube, a 2-dimensional surface, and you can put boundary condition here as we discussed before, and you will have a flux, and you will have here a domain wall. Okay, and the flux is related to the domain wall. So there is a physics to understand the compactification on a tube with flux. Basically, what you need to do is to understand this domain wall picture. Okay, so if you understood this domain wall picture, you already found one entry in this dictionary between 6D compactifications and 4D, and that is the theory corresponding to the tube. It's a very simple theory. It's algorithmic. There is a very well posed question. The only problem is that there is no systematic way to understand what is the theory living on this domain wall. So the way we perform the computation here, we make educated guesses of what this theory can be in terms of a Lagrangian. And in many cases, simple educated guesses work, but not always. In general, this theory might be strongly coupled and we might not know what it is. Okay, so this is a non-algorithmic part of this story. But again, physically well defined, understand domain walls in 5D. Okay, and then the next step is trickier, and I will explain it now. So till now, we have discussed a given 6D theory and we studied its compactification, but now the claim is that in this story, you understood the theory in principle corresponding to compactification on a tube. To construct theories corresponding to more complicated surfaces, we need 3 punctured spheres. Like from tubes, we can only build tubes, right? We can only concatenate them together. But to build like theories corresponding to more general geometries, we need at least a sphere with 3 punctures. Okay, how do you get that? And you get that by constructing, by understanding these tubes for a sequence of theories which are related by 6-dimensional renormalization flows triggered by vacuum expectation values. So let me explain how this logic goes. Okay, any question about the domain walls? For a continue. Okay, so how does it go? Say we have a 6D theory. So we yes?
When you say 6D theory is generically strongly coupled, what does this precisely mean?
This means that we don't have a Lagrangian description of these theories. Any Lagrangian you will write in 6 dimensions will not flow to an interacting theory. Okay, so these 6-dimensional theories do not have a Lagrangian description in 6 dimensions. So they're intrinsically strongly coupled. They don't have parameters. You know, they are not free theories and they don't have parameters. There are no parameters you can tune for this theory to be, you know, described in terms of weakly coupled fields.
Okay. Right, no problem, that's fine. But let me just make sure one statement. Say, suppose, you know, a lot of time you may study non-abelian gauge theory, I suppose. I mean, in 4D we do, but in 6D, if we do study non-abelian gauge theory like Young-Mills,
it will be free in the infrared.
Right. So that's why I say it seems strongly coupled means different thing in 6D layer. And
that's right. You cannot engineer it with a gauge theory. It's
no problem.
It's in a sense a miracle that these theories exist at all. The way we know they exist is by various string theoretic constructions, but not as a gauge.
Yeah. Thank you very much.
Okay, so say we have 2 such theories in 6 dimensions. Again, they are abstractly defined in some way, but in certain cases we know that this QFT1 has some operator, and if we give a vacuum expectation value to that operator, we obtain another quantum field theory in 6 dimensions, another CFT in 6 dimensions. So there is type of a flow triggered by a VEV that we can consider. On the other hand, there is this thing that we discussed till now, is taking this QFT1 and placing it on a compact Riemann surface, on a compact space, and going down to 4 dimensions. Okay, we can often identify this operator that we have given a VEV to with another operator which exists in 4 dimensions. Basically, for example, one can map the symmetries of the 6D theory to the symmetries of the 4D theory and find an operator which has exactly the same charges as the 6D operator that we give a VEV to directly in 4 dimensions. And then we can ask, you know, turn on vacuum expectation value in 4 dimensions. So there are these flows, like flow in 6D, flow between 6D and 4D, and then flow in 4D. And then we can ask, is there this missing part of this diagram? Can we make this diagram commuting, like, you know, either first flow across dimension and then in 4 dimensions, or first flow in 6 dimensions and then go down to 4 dimensions on some Riemann surface. Here I denote it by A and here I denote it by B. And maybe a little bit surprising, but eventually not very surprising fact is that this can be done, this commuting diagram can be built, but the Riemann surface that you can take here is not the same Riemann surface as is here. Basically, the difference between the 2 surfaces is that this surface typically will have more punctures, okay, and why I will explain soon. Okay, the number of punctures that that extra punctures that this surface will have are related to the flux for symmetries under which this operator that we gave F to is charged. Okay, so and then the point of this computation is that if we understand compactification on 2 punctured spheres, studying such flows, interplays between 6D flows and flows from 6D to 4D, we can engineer theories with more punctures. And that's what we want to construct more generic surfaces. So, right. Okay, so okay, my slides mixed up a little bit. So let me give you an explanation of how, why, you know, a heuristic explanation why these flows across dimensions and flows in 6 dimensions generate extra punctures. Okay, so okay, actually, sorry. Let me first discuss this particular case, and then I will give you explanation on that slide. So let me apply this general procedure in a very particular case. So there is a very particular sequence of 6D theories, which are called this DD conformal method, which we already encountered. There was this D4, which is also called the E string. So let us start from this sequence. Compute everything you can about this theory, anomalies, symmetries, and so on. For example, the symmetry for general value of n is SO for n plus 12. For n equals 1, it's SO 16, which happens to enhance to E8. So we can perform this part of the computation. We also can compactify on a circle to 5D and deduce some 5D descriptions of this theory in terms of gauge theories. One such description is in terms of SUN plus 1 gauge theory. So we will expect punctures to have SUN plus 1 symmetry. Again, a version of n equals 1 where we have D4, we already discussed, the symmetry would be SU2. So for general n, the symmetry will be SUN plus 1. And we can also analyze these domain walls and obtain that the theory that it corresponds to a 2-puncture sphere with particular value of flux is this Wezumino model. Okay, this may be ugly looking, but very, very concrete Wezumino model. And again, the way we deduce this is by conjecturing this theory and then checking against 6-dimensional predictions all the anomalies and symmetries and so on. Okay, so this part of the story we know. Just, you know, in this particular case, we can understand the domain walls, so we know the 2-puncture spheres in this case. And now we go to this more tricky part of this relation between theories, different theories, and RG flows in 6 dimensions and between dimensions. So the way it goes in this particular case, and this is again a very general statement. So in this case, we can go between different values of n by turning vacuum expectation values to a very particular operator in 6 dimensions. So we can go from higher values of n to lower values of n. So this is true. What is a VEV? You know, you have a 6D theory, you turn on a constant, space-time constant VEV in this theory, and you go to a different theory. However, you know, since we want to compactify on a Riemann surface, and we also have some gauge fields turned on, some background gauge fields turned on, we might not be able to turn on a constant VEV on the surface. Okay, because, you know, because of this flux, we might need to turn on, you know, a vacuum expectation value, which depends on the position. And this claim is that, you know, we can localize this flux to some small regions on the Riemann surface. Everywhere else, we don't have this gauge field, so we can turn on constant VEV, and this non-constant part of the VEV can be localized in some regions on this 2-dimensional surface. So something funny happens in these regions. And it so happens that in these regions, the number of which is determined by the value of flux, we get extra punctures. And we can understand what type of punctures we get and what are the properties of these special regions. And that's how you know, the extra punctures are created in this process of both turning on the VEV and going between dimensions, between 6D and 4D on the Riemann surface with flux, and that's why the flux is important. And here is a very concrete, I will just very quickly show, you know, how it works in practice. So I have drawn here what is the theory corresponding to a 2-puncture sphere. Now let me take 2 such theories and glue them to a theory which corresponds to a torus. This is basically what is done here. 2 theories corresponding to 2-puncture spheres are glued together, and this is a theory corresponding to a torus for this general Dn plus 3 minimal conformal method theories in 6 dimensions. And then what we do, we turn on a VEV to a very particular operator. Basically, this is the operator built from this field and this field. And this corresponds to a wave we can turn on in 6 dimensions, which will take us from a theory with value of n to the value of n minus 1. Okay, and then it's a very explicit theory in 4 dimensions. We can analyze its dynamics. Okay, we analyze the dynamics. What happens if we turn on this vacuum expectation value? This vacuum expectation value fixes the symmetry from SUM plus 1 down to SUN, and some fields become massive and so on. So we can easily analyze the dynamics, and we get a very particular theory in 4 dimensions after we have given this wave. But now the logic is like that. We started from a theory corresponding to a torus. We given a wave, and we expect to get a theory corresponding to a torus with a very particular number of punctures. And in this case, by general argument, we will deduce that the number of punctures is equal to 1. Again, this is determined by the flux of our original theory and by the particular wave that we have given. And finally, this theory corresponds to a smaller value of n, to a torus with minimal puncture, and we can try to cut this torus into a 3-puncture sphere with 2 punctures coming from cutting the torus, and this 1 additional puncture which we generated by the flow. Okay, and this can be explicitly done, and this is the theory which one will obtain, which corresponds to a 3-puncture sphere. And this is a very explicit, simple gauge theory, which for n equal 1 that we have discussed before, again gives us SU3 with an f equals 6 that we obtained in a different method, like ad hoc method several minutes ago. Okay, so this is an algorithm that one can use to deduce like the compactifications of general theories in 6 dimensions on general Riemann surfaces. It is a method. It's not very algorithmic. Again, the tricky part, the main tricky part is understanding the domain wall theories in 5 dimensions. But it is a very well-defined physical question. Okay, so let me end quickly with stating various comments, more comments about compactifications, and finally stating some open problems. Okay, so we have discussed this procedure of going from 6D to 4D and deducing various dualities in 4 dimensions, emerging of symmetry from geometry of this compactification surface. But there are actually more, knobs and handles that one can play with in this compactification procedure. For example, we have discussed this notion of infrared dualities. It appeared in many contexts in this talk, but there is this another a bit weirder notion of UV duality. So what is a UV duality? UV duality is something which looks maybe rather boring. You have a CFT that you start with, and then you turn on 2 different relevant deformations and flow to 2 different infrared fixed points. So in a sense, you call these 2 theories UV dual. Again, all it means that they come as 2 different deformations of the same theory in the infrared, in the UV. So this thing sounds boring, but it gets less boring if one considers these types of flows across dimensions. So for example, we can start from a CFT in 6 dimensions and compactify it on a circle down to 5D with one type of holonomy or with another type of holonomy and obtain 2 different gauge theories. Why is it interesting? It is interesting because we don't know much about the 6D theory. This 6D theory is some mysterious, strongly coupled gadget. And in this way, we can obtain 2 different weakly coupled descriptions in 5D. Okay. So for example, if one takes this dn plus 3 dn plus 3 minimal conformal method that we mentioned, there are actually several different things one can obtain. This SUN plus 1 gauge theory that we already discussed, a USP2N gauge theory, or Quiver theory in 5 dimensions. But now this is interesting because, as I mentioned, these 5D gauge symmetries can correspond to 2 punctures in 5 dimensions. So now you can have different types of punctures along which you can glue surfaces together. Okay, and using these UV dualities in 5 dimensions, you can build more dualities in 4 dimensions. By, for example, cutting these closed Riemann surfaces, opening these things up into different types of punctures, say SU, USP, or this quiver type of punctures, you can construct different, you can discuss different types of constructions of four-dimensional theory. So here is an example of a simple duality you obtain in 4 dimensions using these types of logic. So SU3 with a field in a symmetric representation, some number of fields in fundamental and anti-fundamental representations is dual to this quiver theory with 3 SU2 gauge groups. And both of these theories correspond to a torus with 1 puncture in particular setup, and the fact that such a duality exists follows from a 5D UV duality of the type I mentioned. So there are really many things that one can do. Finally, we have discussed dualities like in 4 dimensions, between 6 and 4 dimensions, across dimensions, but there also is something that we can call a 6D duality. Okay, so 6D dualities, 6D theories are strongly coupled theories. We can consider turning on vacuum expectation values, but we cannot consider really dualities, you know, interesting dualities between theories in 6 dimensions, like relevant superpotential deformations and so on. But what we can actually do, we can consider 2 different theories in 6 dimensions, let us call them QFTA and QFTB, and compactify them on different Riemann surfaces. They might be the same or might be different. So this is, again, like discussing a theory in 4 dimensions, another theory in 4 dimensions, and turning on different relevant deformations for the 2 theories. And then we flow to 4 dimensions, generically starting with a 6D theory and the surface, different 6D theories and different surfaces, we will end with different theories in 4. But in some cases, we end with the same theory in 4 dimensions. So if this happens, we might call the situation a 6D duality. Yeah. You have 2 different 6D theories flowing to the same 4-dimensional theory in this procedure. Okay, and here are some examples. So, for example, you can take QFTA to be theory living on 6 and 5 branes, and you compactify it on a 3-punctured sphere with very particular types of punctures. And the claim is that you get a very particular strongly coupled theory in 4 dimensions, which is called the E8-Minahane-Meshansky theory. Or you can take this E-string theory that we discussed, compactify it on a torus without any punctures, and then you will obtain, the claim is that again you obtain the same as SCFT. The starting points in 6 dimensions are different, the deformations are different, but the final theory you obtain in 4 dimensions is the same. And here is another example. Take this E-string theory that we have discussed. This is given here on the genus 2 Riemann surface. Obtain this theory that featured several times in this talk. You can obtain the same quantum field theory in 4 dimensions by starting with a completely different 6-dimensional theory, which is called the minimal SU3 SCFT, and compactify it on a 4-punctured sphere. And in the end, the claim is that you end up with the same quantum field theory in 4 dimensions. Okay, so this is very analogous to 4D, say, cyber dualities, but now you start from 6D and you go down to 4D. Okay, so what we claimed is that we can understand these lower dimensional dualities by engineering them geometrically in higher dimensions. But here we have a duality between 6D flows, like starting from 2 different 6D theories and going to 4 dimensions. And field theoretically, there is no higher dimension to go. So a way to understand these types of duality probably is by using string and M theory techniques, but this has not been thoroughly understood till now. So, and final comment is that, as I already mentioned with this G2S QCD, not all dualities that we know about in lower number of dimensions have this geometric understanding. Here is a list of some theories that some very famous dualities like this Kutassov-Schwimmer duality and so on, for which we don't know how to engineer them in these geometric setups. And here are more exotic types of 4D dualities that you can deduce using various methods that we don't understand geometry. So this is, again, I remind you this picture that I have drawn in the very beginning. So we are trying to understand this 4D dynamics or lower dimensional dynamics by engineering these things in higher dimensions, and then going down with this compactification procedure. And a lot of these dynamics in lower dimensions can be understood in this way. But first of all, not everything. There are many open questions here. And second, to fully understand this picture, probably we will need to go beyond quantum field theory to string theory and M theory. Okay? So let me summarize with this outlook with a list of big questions that that I think one has a chance of answering. Some of these questions involve things like the following. For example, we have discussed certain, compactifications of 6D theories on certain Riemann surfaces, and we deduced that they have four-dimensional, cross-dimensional duals in the sense that we have discussed. The question is, do all such flows across dimensions have a lower dimensional dual? A technical question that I did not discuss in this talk, but a lot of these field theoretic discussions in lower dimensions involve gauging of emergent symmetry. Okay, and this is something to be better understood. Do all dualities in lower dimensions have geometric origin? Do all dualities in higher dimensions, like 6 dimensions, have a string theory, M theory explanation? What is the general structure of RG flows in dimensions, across dimensions, and so on? Are all quantum field theories, conformal field theories in lower dimensions Lagrangian, in the sense that you can find a Lagrangian in terms of weakly coupled fields which flows to them? And finally, as I mentioned, in higher dimensions, in 5 and 6, all dynamics, Lagrangian dynamics is IR3. But is there anything we can do to usefully describe these theories, maybe involving a lattice and not a continuous gauge theory? For example, there is this idea of deconstruction that people have discussed in the past. Okay, thank you very much for your attention and patience.
Thank you very much, Shlomo, for the wonderful, beautiful lectures. Really appreciate this. Comments or questions from the audience, please feel free. So let me ask one first. Anyway, people can still ask. So how is this maybe duality is perhaps crossing the dimensions? Maybe in the framework recently done maybe for like people who do swan lane, for example, like a cobordism hypothesis. In that type of picture, are there some maybe some perspective we can take also from that type of
right? Not directly that I can think of. So because of course in that type of questions that people are entertaining, you are asking different type of questions. Like, is there like given a quantum field theory, does it have a UV completion including gravity? Mm-hmm. And of course, in all of this business, I didn't care about gravity. I'm just talking about quantum field theories. Mm-hmm. I don't know if marrying these two questions would be useful or not. I don't know. Mm-hmm.
Actually, another question is that how much do we know the classification of the maybe SCFT in higher dimensions? Maybe it's already quite settled, but I'm not aware the current status. Can you make some comments about this since you start from 60
right. So yeah, so there are classification programs that there are claims that it is complete, and there are claims that there is no proof that it is complete. But for example, you can try build field theories, starting with F theory constructions and M theory construction. And you can classify all the possible, plausible constructions coming from these higher dimensional setups, string theoretic and M theoretic setups, like all the possible things you can think of which will give you a 6-dimensional CFTs. So this was done by Kumrun and collaborators, many collaborators, Jonathan Ekman and so on. And similarly, so there are many things which can be done. Of course, there is always a question, can be something done not in this framework? And, can you build something outside of this framework? But, taking particular types of constructions, there are claims of complete classification, given that those types of constructions. Another interesting question that people are entertaining also, it's a very, very fruitful endeavor, is like, what are the 5D theories? What are the 5D CFTs? What are the 5D gauge theories that you can write, which are UV completed by 6D theories, which are UV completed by 5D SCFTs, and so on. And so these are very important questions, as a starting point to the whole story that I was telling you. This type of answers to these questions are input to this type of consideration. So you find a 6D theory, you can characterize in some way, and then you can start going down. But of course, understanding the full spectrum of 6D theories is very important, and also understanding the 5D theories is very important, because 5D theories give us these punctures, this how we can glue surfaces together. Okay. So understanding the full set of possibilities is extremely important for this type of constructions.
But we know the labels of the 6D SCFT in all general grounds. How do we know the data we need? And also, for example, maybe people are more thinking about the defects and of extent defects in the.
That's right.
CFT. So maybe those data.
Right. So there are various techniques to determine. For example, one of the ways to construct these theories in 6 dimensions, okay, is to consider gauge theories in 6 dimensions and think of them as, like in 4 dimensions, when we are discussing n=2 theories, we can go on a Coulomb branch in 4 dimensions. And on a Coulomb branch, we have these IR-free gauge theory descriptions. Okay? In the same way, in 6 dimensions, we can go on what is called the tensor branch, which is analog of this Coulomb branch in 4 dimensions. And then the theories are described in terms of gauge theories on this tensor branch. So this is not a CFT point. This is kind of a deformation of the 6D theory. And you can try to compute anomalies for various symmetries by matching them, by computing them on these branches and matching them with a fixed point. And there are string theoretic techniques using which you can compute various anomalies and so on, and deduce existence of certain defects, which are certain branes. And there are these highbrow techniques to deduce things. Like, for example, what are the higher form symmetries of these theories and so on. Okay, so there is a large industry deducing that. And once you understand those type of properties, you of course can try to embed them in these compactification scenarios. So if the theories in 4D are n=2 supersymmetric, there is quite a bit of literature on trying to understand these higher form structures and higher group structures in 4 dimensions, starting from 6 dimensions. For example, there are a lot of works of Sakura, Shaffer-Nameki, Lakshya Bhardwaj, and friends on these types of questions. But in these n=1 setups, more generic n=1 setups, much less has been done. There is a lot.
And how do we know the data? What's a complete set of data to label or classify?
Complete set of data, of course, we don't know. Also about these 6D theories, we can deduce some skeleton, For example, you can ask, if I give you a known, like conformal anomalies, does it specify the theory? We know in 4 dimensions that specifying, say, A and C anomaly doesn't uniquely specify the theory. Okay, I can build theories, say, which do not have global symmetries, and they have the same A and C anomalies, but they are not the same. Okay, how do I know that they are not the same? For example, I can compute a supersymmetric index, and the supersymmetric index of the 2 theories is not the same. Okay. So what is the minimal, data, even in 4 dimensions? Forget about 6 dimensions. It's not known, It's a very interesting question. Like, is there a minimal set? Like, you tell me, what do you need to tell me in order that, the theory will be, like the skeleton will also tell you what the meat is. Like, how do you fix that? I don't know. Okay, and you know, and also in the higher dimensions, you can ask the same question, but I don't know even the answer to this question in 4 dimensions.
Okay. Thank you very much. So I think the classification maybe is done only in the formal side, in the procedure, but not in the data. I suppose that's what you say. We don't know the complete data yet. We may know the procedure to obtain some of those theory.
Yeah, I think that's a correct statement.
Any other comments, questions? Okay, if not, I think we should thank Shlomo again. Thank you very much. Really appreciate it.
Thank you very much.
Thank you, Shlomo. Thank you.
Bye.